Welcome. It's my pleasure to introduce today's speaker, Dr. Brian Miller. Brian has had a lot of different affiliations with the College of Optical Sciences. It may, in fact, even be a record. He got his bachelor's, master's, and PhD here. No big deal about that. While he was an undergraduate in the optical engineering program, he worked as a student helper in my group, originally preparing the figures for Foundations of Image Science. But it quickly became apparent that he had lots of good ideas for research, and we took advantage of his skills even as an undergraduate. He went on to his graduate work and then to a postdoc position, and now he's an adjunct assistant professor in optical sciences. He was both an RA and a TA during his tenure as a student. Tenure as a student, that's a good concept. But Brian got through the program very efficiently. And very successfully. He was, I believe, the first optical sciences student to be honored as the student innovator of the year for the entire university. He developed a technology at that time that he's going to tell you about today. At the time, we called it bazooka SPECT. Brian calls it something else. He calls it iQID, but I don't do that. I don't want to be the one who gets sued by Apple. But he was also the founder and the international director to this day for BUG, which stands for the Bazooka Users Group. It has chapters in Brazil, Sweden, England, Ireland, Germany, and no doubt other places. And Brian travels around to all these places, showing them very innovative ways of using the iQID technology. Now, this is a nuclear medicine technique, and many of you have seen nuclear medicine images. Over the years, we've developed a standard apology for nuclear medicine images. We say they may be blurred and low resolution and noisy, but they give us the information we want to have. Brian's not going to use that excuse. I trust you'll agree at the end of this presentation that his images are beautiful. That's a term that we don't normally use in medical imaging, and certainly not for nuclear medicine imaging, but judge for yourself. Brian?
Thanks for the introduction, Harry. It's great to be here. I think you came to Optical Sciences Center first time in 2002, I believe. And the first thing that I remember getting off the airport and seeing the nice weather, and had that same experience again as I got off the airport, and being another part of the country that's freezing cold. So it's great to be back and in this area, and a lot of nostalgic experiences here with great people to work with over the last decade or so. So I'll go ahead and just start off with Harry gave an overview of the detector that I've worked on these last few years, and I'm going to talk about some upgrades and new applications I've been investigating, all kind of around the theme of how we can use this detector for some medical imaging applications. And just to give a little bit of background where I'm at currently, it's at Pacific Northwest National Laboratory. It's one of 10 U.S. DOE national laboratories, and it's located in southeastern Washington, over here in the Tri-Cities area of Richland, Pasco, and Kennewick. And it has some historic significances. It was an area during the Manhattan Project where a lot of facilities were built and reactors. During that time, Pacific Northwest National Laboratory came to support that infrastructure that was there. And now it has missions and applications in national security, homeland security, basic sciences, energy and the environment. And there's some 4,700 staff, I believe, there, and a large capability. It's about 3 hours from Seattle. So typically when I tell people I'm in Washington, they think it's a nice green area, where this is actually a desert area. All the water is gone by the time you get over to that area. It gets less rain than Tucson. But there are 3 rivers there, so I'm excited to see some water there. But so I'm there right now as I have a Linus Pauling postdoc fellowship, where I've continued to investigate the use of this detector technology that I worked on as a graduate student. So just to give a little bit of introduction before I dig into the meat of the detector, which I call the iQID camera, I'll start off with describing a little bit about ionizing radiation as some background if you're not familiar with that, methods that we can detect that ionizing radiation, some medical imaging applications, and then some of the imaging methods that are possible to image this type of radiation. And then I'll discuss some of the applications that both here as a graduate student at Optical Sciences and the Center for Gamma Ray Imaging, and now at Pacific Northwest National Laboratory. So just a bit of background about ionizing radiation. So at the beginning of the 20th century, scientists started discovering that there was a form of radiation that they could detect. And Ernest Rutherford decided to coin the type of radiation based initially off the penetration it could provide. So here we have the first one is an alpha particle shown at the top, where you notice that a sheet of paper could stop this type of radiation. Nowadays we know that it's a helium nucleus that's ejected from the nucleus at very high kinetic energy. The next type of radiation he coined was beta particles, denoted here with a beta. And those could be stopped by a little bit thicker piece of material, for example, some aluminum. It could penetrate it, but it lost significant energy during the process. And then following that were gamma rays, shown here, which are photons. And notice that those took even more material to penetrate. And gamma rays, many are familiar with X-rays. They're similar in terms of they're both photons. They have similar energy, but a lot of times they're distinguished based on how they're formed. So gamma rays are emitted primarily from the nucleus, whereas X-rays you can think of as changes in the electron structure. And then also neutrons were later discovered, and those can be detected as they interact with lower density materials, such as hydrogen atoms and plastics. They can slow down, they can interact with protons, recoil, and then also can be captured. So these are some of the ionizing radiation that we're interested in looking at. One method for detecting this ionizing radiation is the use of scintillation crystals. So a scintillator is a crystal that has typically impurities that are mixed in with the crystal structure that create a band gap and a number of excited states. So within this band gap, if you have a charged particle, it'll interact with the crystal structure, excite electrons to these states here. The decay of those electrons will then emit a photon. And ideally, the crystal will be transparent to this photon that's emitted, and you can then detect the light that's emitted. So here's a crystal that's illuminated with a UV source, and we're able to see fluorescence. You can imagine that now you could have a charged particle that's going to excite atoms within this crystal and also give off light. There are a number of scintillators, literally hundreds that are available for different applications. Some of the common ones that are used in a number of medical imaging and other detector technologies are sodium iodide, cesium iodide, and you can see here there's a range in the number of photons per MeV that are detected. One of the first scintillators that was discovered was zinc sulfide, shown here. It's one of the brightest. And I'll talk more about this later, but this has close to around 100,000 photons per MeV. Now, there's a number of uses of ionizing radiation that stems back to around the 40s, where they realized that if you could take a radionuclide, attach it to a ligand, a label, and then inject it, you could use that then for understanding molecular processes that occur within the body. So we see here we have a radioactive atom that's attached to this ligand. That can then be injected. It will migrate to receptors on cells and then begin to emit photons. So in contrast to when you think of X-ray imaging, we have X-rays that will go through the body and produce an image of that the attenuation of the X-rays through the patient. Here you have the source that's inside of the body that can emit radiation, and we can use that to image and understand the biological processes that are occurring. And there are a number of imaging modalities that are possible. So have here over on the left X-ray CT, and you also include here MRI, which you can think of that they allow you to see the anatomy of the patient, where the structure is, the bones, that sort of thing. But these other imaging modalities that utilize ionizing radiation, in the case for gamma rays, we have SPECT imaging, which here's a brain scan. So this is a tomographic image where we can take slices and see what the distribution of that pharmaceutical is inside the body. There's PET imaging, which stands for positron emission tomography. So a positron you can also think of as a beta particle, but so beta particles are noted beta plus, beta minus. Beta minus incorporate electrons, beta plus are positrons. And a positron is the antimatter companion to an electron. So a positron will interact with an electron. The two will annihilate each other and emit two gamma ray photons traveling in directions 180 degrees apart from one another. These are in vivo imaging techniques that are used. Another technique, in this case this is with charged particles, is autoradiography. So this is ex vivo, where you have a slice of brain here and you're imaging what the distribution is of that radio tracer inside of the body that was injected. There's also a technology that is called Cherenkov imaging. And so when you have a particle that's traveling faster than the speed of light inside of a material, it'll produce light. And so here's a technique that's now being investigated where you can image that light and see what the distribution is inside of the body. So how do we form images of these particles and these gamma ray photons? Well, one technique is with pinhole imaging. So we have here an image of a pinhole camera. You have a box that has a small hole in it. You can use this technique, as many of you well know, to form an image. So if you put a piece of film here, a photographic emulsion, it takes a long time if you're not using lenses, but you can still produce an image of the object. You can do the same thing with gamma rays, but your pinhole needs to be a little bit different. It has some more characteristics related to, in this case, gamma rays. So we have here, in this case, this is a mouse that has been injected with a radiopharmaceutical that has preferential uptake in the bone. So we have here this mouse that's emitting gamma rays, and here we have a pinhole aperture that needs to block all of the gamma ray photons except for those going through the pinhole. So those pinholes are typically made of high density material, lead, gold, platinum. You have here a detector where you detect the individual gamma ray interactions, and then over time you can build up an image. So what we have here is an image of the skull of the mouse. You can take this imaging technique and do tomography with it, 3D imaging with it. This is done by, shown here, we have the mouse. We've rotated and acquired a series of projections at different angles and acquired a data set. You can take that data set and then from that reconstruct the 3D volume of that object. So with that brief introduction, I'm going to talk about what we call the iQID camera. So originally this was called bazooka SPECT, but now to incorporate its broad response to other forms of particles, we've called it the ionizing-radiation or intensifying, as well, Quantum Imaging Detector. So the graduate work I did here at the Center for Gamma Ray Imaging in College of Optical Sciences was primarily centered on the use of gamma rays and X-rays. So for medical imaging applications, there's a range of gamma ray emitters that are useful, each with different properties depending on their energy of the gamma ray photon, and then also their half-life that are related to when you inject them. You don't necessarily want something that's going to be around forever, and so there's a number of isotopes that are available for use. And the iQID detector, it relies on the use of a new type of structured scintillator. I showed before a scintillator that was a monolithic crystal. Here we have a scintillator that's been grown in a custom fashion and allows us to perform very high resolution imaging with our detector. So we have gamma rays here. Here's a columnar structured scintillator. Here's a magnified SEM image of that crystal. And these are grown in a needle-like structure. So this has the effect of, as a gamma ray interacts, it'll produce a flash of light. That light, via total internal reflection, will migrate towards an exit face of the detector. We couple that to a detector, in this case a CCD camera, and we can see individual gamma ray photon interactions. So what you're seeing here, each little flash of light that you see is a single gamma ray that's interacted in the crystal. We have collaborations with a group called Radiation Monitoring Devices that, in addition to cesium iodide, that was a previous detector, there's also investigating other types of scintillators that have different properties. In this case, this is a lanthanum bromide. Again, each flash you see is a single gamma ray interaction. You can get very high spatial resolution with this detector if you identify and estimate the interaction of each individual gamma ray photon. So these two images shown here, the first one on the left is where we've identified each gamma ray photon, estimated where it interacted in the crystal, whereas here on the right we've just taken all the light that's produced, haven't identified each individual one, summed it up, and here you can see the two cross sections, the profile of those. So if we estimate each interaction, we can get much higher spatial resolution. So that's really a key concept with this detector technology, that if you identify and estimate each detector, you can get very high spatial resolution. So here's a little bit of describing the algorithm that we use to identify and estimate the interaction of each gamma ray photon. So here's a CCD frame shown here, and in that CCD frame there are 5 gamma ray photons shown here. We first take the image, we filter it so we remove hot noisy pixels, and then we identify each interaction and the pixels associated with it. We then take those extracted pixels and then estimate where the interaction occurred. So here's a exploded view of the first what we called bazooka SPECT detector. Originally it was a very massive detector, so the name fit quite well, even though now it's much more compact. But really one of the key components in the device is the use of what's called an image intensifier, shown here. So this is a night vision device that's used in military applications. And the simulator, which I showed before, gets coupled to this entrance face of the detector. That amplifies scintillation light. You have an exit screen here, which then gets imaged onto a CCD camera. And then these images here show the detector being illuminated with different types of gamma rays. Here we have iodine-125, which has lower energy gamma rays, around 30 keV, compared to technetium-99m, which has 140 keV gamma ray photons. And you'll notice that the individual flashes here are a little bit brighter compared to the lower energy gamma rays. And here's a tomographic reconstruction of kidneys from a mouse. So I mentioned the image intensifier is really one of the key components of the device. I'll describe that in a little bit more detail. Here's a schematic that shows an image intensifier. So you have your lens, if you use this as a night vision device, that will take a low light level scene, something at night. Photons that are produced from your scene will get imaged onto the face of this detector here, a photocathode. The photocathode converts the optical photons into photoelectrons, and then those are amplified with a microchannel plate. That microchannel plate then takes the electrons and they impinge on a phosphor screen, and you can get gains ranging from 10 to the 5th or 10 to the 6th or higher, depending on how many microchannel plates you have. And over the years, the iQID or bazooka SPECT detector became much more compact, so to the point where it no longer resembled a bazooka anymore. It uses more scientific grade custom image intensifiers, as well as CCD cameras. And really the image intensifier is a key component, because what it allows you to do is everything downstream from here. If you amplify that low light level beforehand, you then have the flexibility to choose whatever sort of camera or sensor that you want to work with. So what we have here is an iPhone that's serving as a gamma ray detector. So each flash you're seeing is a single particle that's being detected. And there's also an app that we use for an Android as well. So both are available. Now, a key technology that has emerged around the time we started investigating these detectors is the use of graphics cards. So if you're going to be using very fast cameras and identifying each individual event, storage of the frames becomes an issue. And if you want to process this in real time, it also becomes a challenge. So the group at the Center for Gamma Ray Imaging has invested heavily, a large portion of the R&D efforts, to utilize graphics processing cards. And these are great. So you have a gaming industry that's fueling the design of very fast, massively parallel cards with thousands of processors that can perform operations in real time. So that previous algorithm I showed you where I identify each event, that's done in real time using these graphics cards. And a key attraction of these detectors is the relatively low price that you can get. Something that has, almost 2,900 cores for less than $1,000. Now, one of the methods, area is important when you have a gamma ray detector so that you can have a relatively large imaging area depending on what your application is. But there's a technique that you can use for increasing the active area of the detector, and that's using fiber optic tapers. And these are a very interesting type of devices. It's you can imagine it's a large bundle of optical fibers that are heated and fused together. If you then stretch those and cut and polish the ends, shown here, depending on which way they're coupled to an imaging plane, will either magnify or minify. So we take this small end here, we couple it to the large end of our image intensifier to get a much larger active detector area. So shown here is one of our iQID detectors using a 4:1 fiber optic taper, which has a 25 millimeter output, a 100 millimeter input face, and that gives us a 16-fold increase in detector area. We spent quite a bit of time looking at how we could take these detectors and couple them to larger scintillation detectors, and we did this in collaboration with RMD. So I'm going to describe an imaging technique that uses this large area scintillator and our large area iQID detector. And I showed before that one method for imaging gamma rays is to use pinholes, but you can also use what are called parallel hole collimators. So here's an example of a parallel hole collimator. And you can imagine a large bundle of, if you were to take a large bundle of soda straws and look through it, if you were to look straight through it, you could see an image of an object. Same thing here. So only gamma rays that go straight through or at normal incidence get detected. But you can take an object, couple it to the front face of this image apparatus, and then do high-resolution imaging. Depending on the size of the bore or how wide these holes are will determine the spatial resolution you can get here. So here we have a relatively coarse array of these, in this case they're made out of tungsten holes. Here we have a very fine grid. So we use this imaging technique to do what's called dynamic scintigraphy. So we're just producing planar images of an object. And here's an animation showing this technique. So here in this setup, we have a mouse that was injected with a radioactive tracer that targets primarily growth areas of the bone, so joints, knees, skull. And if you watch this, you can see the uptake of the radiopharmaceutical. So injection starts to fill the bladder, but then over time you start to see a large amount of uptake in the skull and other regions of the object. Again, this is planar imaging, 2D imaging, but allows us to be able to identify each event, go back in time, and then figure out what the uptake is at various times. Here's another image. In this case, this is a radiopharmaceutical that's used to look at the uptake of a tracer in the kidneys, shown here. Here are the over here at the top. They're the uptake. And these are 1 second per projection. Down here are 10 seconds. And you can then use this information to track what the uptake and washout of various pharmaceuticals are, shown here. So if you look on the bladder up here at the left, you have relatively low uptake, whereas the kidneys you get a very large spike and then tapering off as the activity goes into the bladder and other organs. Here's an image. In this case, this is with a larger animal. This is with a rat. So these are 30 seconds per projection, but you can see the uptake up there at the top left, right at the start, and then an eventual uptake in the bladder and kidneys. Another way to do imaging is with the use of coded apertures. So what we have here is with coded aperture imaging, the idea is that you can take, if you have a planar source, this is used heavily in astronomy. You want to collect as many photons, many gamma rays as you can. The challenge with if you have a single pinhole you may not get as many gamma ray photons as you'd like. That translates and may take longer to do an imaging acquisition. There's a way to increase that capability by having many pinholes, but arrayed in a certain pattern, which we call a coded aperture mask. And if you have a single point source, here we have a bead that's 50 microns in diameter, that will produce an image on our detector of the points of this coded aperture mask. You can then take that projection image and use a decoding mask and reconstruct that object. So we wanted to use that technique to apply it to gamma ray microscopy, shown here. So here's a coded aperture that was laser drilled in platinum foil, 25 microns thick, with pinholes that are 25 microns in diameter. So in this mask here, it's about 1 millimeter by millimeter, it has almost 700 pinholes. To test this technique, we made a phantom image consisting of these individual beads, 50 micron beads. Each bead will produce a copy of that code aperture pattern. If you look at a bead next by, that'll produce the same pattern but shifted. And then what you have here is a multiplexed image. You can use that decoding technique to reconstruct your object. So here the estimated reconstruction resolution we're looking at is about 30 microns. I talked about earlier, if you want to do the tomography with these techniques, you can either rotate the mouse, acquire different projections, but you can also, another method is to surround the object with many cameras. So at the Center for Gamma Ray Imaging, there's been a large investment to produce stationary systems that surround the object with many detectors and acquire projection images simultaneously, and we call this technique FastSPECT. So the FastSPECT 1 system that uses 24 cameras, the second generation, FastSPECT 2, used 16 conventional gamma ray detectors, and the latest is the FastSPECT 3, which uses 20 iQID cameras for high-resolution imaging. Here's an image of the system. This is the processing unit shown here. It's, with the use of graphics card, it was close to 20 teraflops of computing capability. It would process total 4,000 images per second. And then here's the reconstruction and the readout system. Here's a side view of the cameras. Again, each camera is running about 200 frames per second. It takes all that image data and processes it in real time. So designing this system was a challenge, but it was a lot of fun as well. We were able to look and utilize new types of technologies for being able to produce components. One of the key things was being able to produce the imaging aperture that would be used to project 20 projection images onto the cameras. And so at the Center for Gamma Ray Imaging, we have a 3D printer here that allows us to print objects in molds. And here's an image of a fabrication procedure we came up with making tungsten composite apertures. So the idea is that you can take a mold, print the mold, mix tungsten powder with an epoxy, pour that into the mold, and you can cast relatively high density imaging apertures. I mentioned you need to have a pinhole that's going to have a high density material to stop the gamma ray photons. Another interesting type of material that's available is one that's flexible. So on some of the molds, you need to be able to remove the inner structure. That becomes difficult. And one technique we found was to use these flexible, almost like gummy type of gummy bear type of texture, which we could then cast the material and then extract it. It's also possible to use the technology to make pinholes. In this case, these are pinholes with very complex geometries. We printed the pattern for it, cast them in platinum, and here we have a pinhole with a 200 micron diameter hole. And this is the individual components of this imaging aperture for the FastSPECT 3 system, the pinholes and the pinhole aperture installed in the frame. And so what we get, the combination of these technologies, is an interface which allows us to acquire all the projection images simultaneously. Here was a resolution phantom that we wanted to see what the overall spatial resolution of the system is. And we took this phantom with the smallest holes here are 350 microns in diameter. Those are filled with a technetium radio pharmaceutical and inserted into the holes. And these are 20 projection images acquired from the cameras. Again, we take those series of projection images and can use them to reconstruct the 3D object shown here at very high resolution. So when I joined Pacific Northwest National Laboratory, one of the things I was interested in doing is now taking this iQID detector and looking at other sources of radiation, seeing how we could image those, how the detector performed, and new applications that would come from that. Here's the detector that I built there, and one of the goals was to make this very portable so we could take it and visit other laboratories who are interested in some imaging applications. It runs off a laptop with a very nice GPU. This is it's an image intensifier that has a 4-centimeter diameter. It can be coupled to a fiber optic taper that gives us an active area of 125 millimeters. And the detector that's currently used are point gray CCD cameras. So this has been an interesting technology. As an undergraduate, we had a senior research project where I first became involved with these type of cameras, working with Dr. Hong Hua here. And it's ever since the capability of CCD cameras has increased. Now they're using them with USB 3.0 cameras. So you have megapixel cameras that run at 150 frames per second, close to 500 frames a second at reduced resolution, but they're also very low cost, less than $1,000. And with these detectors, you can get very high counting rate capabilities. The latest recent one in the last few months is a 4-megapixel camera that's a 2048 by 2048 that runs at 90 frames per second. So when that CCD camera is coupled to the 4-centimeter active area, you have roughly 20 micron pixels. For the large area, that provides about 60 micron pixels across the entire area of the detector. So a little bit of history is I mentioned I wanted to go and look and see what the response of this detector would be to alpha particles, beta particles, and others. And one of the scintillators for being able to detect alpha is the traditional scintillator is called zinc sulfide. So this has its roots back to, again, the beginning of the 20th century. And Sir William Crookes, he came up with a device called the spinthariscope. So the idea was that at that time, he was looking to get some radium salt, that they knew that radium was radioactive, but it was also very, very expensive. So apparently he had spilled some of his radium, and he knew that zinc sulfide was a scintillator that could detect this radiation. So he used this detector in a dark room, was able to find this radium salt that he had spilled, and noticed that he could see individual flashes. So he came up with an idea to look at that, and where he coupled a lens, had a radium source here, and then a zinc sulfide screen. And if you would take this into a darkroom, you could see the individual flashes. And this became a very popular device in the early part of the 20th century. It continued to gain popularity so much that it was eventually available as a kid's toy from a cereal box. So all you had to have was 15 cents and a Kick cereal coupon. You could buy one of these spinthariscopes. This is a Lone Ranger ring that had a plutonium-210 source. You'd unscrew this little cap here, you'd stare at it, and you could see these individual alpha particle disintegrations. And this is a more modern one that's currently available. So some of you may have seen these devices, or maybe have gotten them as kids. So I used the same material, the zinc sulfide, this historic material, and decided to see what the response would be to alpha particles with the iQID detector using a different source. This is californium-252. And californium-252 is an interesting material. Isotope. It emits alpha particles, fission fragments, neutrons, and betas. And we created a source by taking small drops, about a becquerel or about a decay per second, drops of this californium-252, and then stippled across this zinc sulfide screen. So again, with californium-252, about 97% of the decays you get are alpha particles, this helium-2, helium-4 nucleus, and the energy of the alpha particle is around 6 MeV. Now, about 3% of the decay is spontaneous fission. So you get daughter nucleus that have mean energies of 80 MeV and 105 MeV. And when we coupled the detector, this is what we got, some of the first images. So what you're seeing here is each little flash, again, is a single alpha particle that's being detected, and occasionally you'll see a very bright flash. And that bright flash are fission fragments. So here's an image, frame taken from that data set. This here on the left shows essentially the light spread of those alpha particle and fission fragment interactions, and here shows the amplitude of the signal that's there. So not only alpha particles, we started looking at neutrons. Now with neutrons, there's different materials that have a large cross section for being able to capture the neutrons, and then products of other particles are emitted, which you can use then to detect. So zinc sulfide screens can be mixed with a lithium-6 fluoride material, a powder, and in that reaction, the lithium-6 will capture a neutron, and the products of that are an alpha particle with about 2 MeV of energy and also a triton with about 2.75 MeV. So what you're seeing here in this image are individual neutron interactions. Neutrons can also be detected with another material called gadolinium 155, 157. This is a material called gadolinium oxysulfide, which is typically used in X-ray phosphors. And here's a material that we wanted to test to ensure that it's not as sensitive. So in this product, you get what are called conversion electrons. So much lower energy, 29 to 246 keV versus the MeV type of particles, but we're still able to detect those with neutrons. Here are betas. So as a beta travels through the scintillation, we're able to observe the track that it makes here. So each image here is an individual beta particle that's interacting with the scintillator. And going back to that initial source we made, this is an image that we got with the detector. This is required over several hours, so about a becquerel per drop, but we're able to image the distribution of that tracer at high resolution. And again, just to emphasize the point earlier that I made, is if you take and just add the light, you don't identify each individual event, you have essentially a blurring effect. You're not able to see the distribution of the source as well as in comparison if we're identifying each individual particle. And because we're identifying each individual particle, we can also estimate where the interaction occurred to a subpixel region shown here. So here's estimating that the alpha particle interaction to a single pixel and then to a subpixel. We're also able to quantify the activity shown here. So this scale bar is in units of millibecquerels, or decays per thousand, every 1,000 seconds. The detector also has the capability to discriminate between different particles. So here's another source we fabricated, again, here with a californium source, which emits, again, alpha particles, fission fragments, neutrons, beta particles. Americium-241, shown here with the A, emits gamma rays, alpha particles. And here, in the form of an S, is strontium-90 and yttrium-90, which primarily emits beta particles. If we take and extract each individual event, estimate its energy, here in the case for alpha particles and for fission fragments, we get these two spectra. We can then apply a threshold here to distinguish between the alpha particles and fission fragments. So what we have here, this is an image showing the spontaneous fission. This is an image showing the alpha particle decay. And then shown here is the decay of beta particles. It's probably a little bit hard to see, but there's a very weak C. So when you have spontaneous fission, you also get neutrons. Or neutrons and beta particles, and we're seeing the beta particles. So once we were able to validate that this thing worked well for looking at other types of charged particles, started looking for what sort of applications could make use of it, and was able to find out that there's a large number of alpha particles that are currently being investigated for medical imaging applications for a field called radioimmunotherapy. So the idea is that there are certain types of cancers, many of them blood-based, that after chemotherapy, there'll still be residual amounts of cells in the body. Eventually, since chemotherapy doesn't get rid of all of them, you'll have these residual cells will eventually come back in maybe 5 years or some period of time, and they'll come back and many times become radiation resistant. So there are groups that are investigating the use of alpha particles where they want to take an antibody, attach to it a radioactive alpha particle emitter or a beta particle emitter as well, inject it, have that home in to the cancer cells, bind to the cells, emit alpha particles, And because of alpha particles, I showed earlier, the range is so short that a sheet of paper can stop them. But if they're tightly bound to the antibody at the site of where the tumor cells, they can irradiate the tumor cells and kill them cell by cell. So that's a promising technique that they're currently investigating. There's a range of alpha particles of interest that have relatively short half-lives. There's one that has recently entered the, received clinical use from the FDA, radium-233. This is a tracer that's used for in prostate cancer. Near the end of the patient's life, they will develop a lot of cells throughout the bones. The bones become brittle, break, very painful procedure. But this is an isotope where you can inject. It goes primarily to calcium sites. It acts like calcium chemically and is able to alleviate a lot of the pain associated with these. These other isotopes I mentioned are for some of the blood-based cancers, myeloma, leukemia, that groups are interested in. So about a year ago, I became involved with a group that was working in this technique at Fred Hutchinson Cancer Research Center in Seattle, where they're using astatine-211, which is an alpha emitter that has a half-life of about 7 hours. And right now they're doing primarily preclinical imaging. So the challenge is when you're using these alpha particles, because they work so well, they're very potent at killing cancer cells, but they also can go to other parts of the body. And that's important in understanding what the dose is going to be to non-targeted organs, such as the liver. They want to optimize how much dose to give the patient before other symptoms kick in that you don't want. And so understanding where they go and what the dose is an important tool that they need. And understanding this at the suborgan level. And so they've developed a number of models to do this, but the imaging capability they had to find these wasn't there. So I started working with them. And here's an image that we took of a biopsy from bone marrow, shown here. So this is a slice of bone marrow that's 10 microns thick, and then a lymph node that was extracted and sliced into 10 micron thick sections. This is an image of the distribution of the radiopharmaceutical. This was at a time point 19 hours after the injection. And I'll show some more images of this shortly. And what's interesting is, especially with some of these isotopes that have relatively short half-lives, since you count each individual particle, with each particle gets tagged the time at which it was detected. You can take that information and you can see you start to begin to get a decay of that isotope. You can then back it out and then find out what the activity was of that isotope at the time of the biopsy, shown here. So here's shown here on the left is the distribution of the alpha tracer. This is an H&E histology slice. And this is 2 hours after injection into the patient. The scale here, again, is on units of millibecquerel, so very, very high sensitivity compared to any other imaging technique with these alpha emitters. This is you'll notice the distribution across the whole area. And then around 19 hours, we see a very high uptake near the periphery of this section of lymph node. Here's an image of a section of a spleen shown here, and the histology slice on the right. And what you can notice in terms of there's regions where you have very high uptake in a localized region. If you were to use dosimetry methods where you just compute the average, it's not going to tell you the whole picture of what's going on. So the goal here is to do microdosimetry, estimate at or near the cellular level what the dose is for the object. And here's a tumor cell, tumor masses that was extracted and cut into slices, shown here. So another project that I started working on recently, this is in collaboration with the University of Medicine in Mainz, Germany, was to investigate a chemical called thorotrast. So this, back around the 20s or 30s, you had radiography where you could take x-rays of patients. You could see if there's a broken bone. But the technique of angiography had come into play where you could then inject a relatively high-density material and you could see where the blood vessels would be. So a chemical called thorotrast, which was thorium-232 dioxide, was used as a contrast agent, primarily in angiography studies involving aneurysms. So the doctor could inject it, they could see if there had been a ruptured vessel, and it worked quite well. The problem with it is it had very high uptake in the liver, the spleen, the lymph nodes, and it's an alpha emitter with a very long half-life. So this stuff would get injected, and it wouldn't come out. It would go to the liver and have a biological half-life for 22 years, so it would be with the patient for 15 years. But what they started noticing is after they did this procedure, about 15 years later, you'd have patients that would come and have liver cancer or leukemia, a 100-fold increase of liver cancer, 20-fold increase in leukemia compared to the general population. So it became a big problem, but was around till the late, in some cases, late 50s. And one of the studies that the group I've been working with in Germany, they're interested in going back and taking slices from previous patients to understand what the dosimetry was to the patient, what the uptake was into local regions, and try to understand the cellular mechanisms. Some cells seem to have a higher radiation resistance response, others not. And we took sections of tissue shown here. This is a section of spleen, and you can see these bright spots as the distribution of that alpha emitter in the patient shown here. And here's in liver. So it's a bit probably faint here, but there's very kind of a lightish pink correspond to regions where the cancer had developed. And you can start to see along those regions where the uptake of this thorium was at. So it's a method that we're able to use this data set, based on unfortunate circumstances, had 15 years later caused individuals receive cancer. But it's a way that we're now able to look at and see if there's information we can glean from those patients to help understand more of the processes that are going on with regards to cellular radiation resistance, things of that nature. And again, here's a magnified region of that spleen. With this iQID camera, we're able to estimate the activity down to 10 millibecquerels. And from this, the next phase will be to estimate what the dose is to these regions at very high spatial resolution. They're approaching cellular level. The other application that we're looking at is now with using beta particles. So positrons, betas, electrons that are emitted, and using a similar technique. So here's a frame of, in this case, a beta emitter that's used quite a bit in the clinic is lutetium-177 and yttrium-90. Yttrium-90 has a beta with an endpoint energy of around 2 MeV. It's maximum energy that emits. Whereas with the lutetium, it's around 500 keV. And so here are extracted beta tracks from the decay. And in collaboration, again, with Fred Hutchinson Cancer Research Center, we're able to image the distribution of the beta emitter. This shown here in the configuration where we're using the 4-centimeter detector. This shown here using a larger detector where we're able to accommodate a large number of tissue sections. And here's an image of extracted sections. Here, these three columns are lutetium-177. Here on the right, yttrium-90, and of slices of kidney. I believe these are liver, and then these are tumor. So the antibody that they were using in this case was CD20, labeled with lutetium and yttrium, and they wanted to see high uptake in the tumor compared to other tissue sections. And here we see it's saturated, and here shows more of the distribution of the lutetium and yttrium, where you have nice uptake in the tumor. So just to summarize some of the benefits and features of the iQID detector, it has been able to show that it has a very broad sensitivity to ionizing radiation from beta particles, alpha particles, neutrons, fission fragments. Really a valuable feature of it has been the real-time dynamic imaging capability. So we can put a tissue section down on the detector and immediately watch an image form in real time. It's a portable device that we can take, and that's been very useful in working with collaborators who are interested in having the detector and the remote capability of it. It's not cooled. It uses many of the off-the-shelf components, so it's easy to assemble and to configure towards a given application. Very high spatial resolution, where we can estimate the resolution to sub-pixel levels, and a very large detector area. There's no detector read noise, which it's a feature that's, I think, one of its most powerful features, where we're able to identify each individual event. We threshold any noise associated with it, and where the pixel value corresponds to the number of decays that occurred at that pixel. Has very high counting rate capability with hundreds of frames per second, and we can extract temporal information to estimate what the activity was at a given time point, and we're able to quantify that activity at very high accuracy. And some of the future work we'll be working on is to take, in particular with alpha particles and beta particles, here we have sections of kidney, and to improve the spatial resolution of beta particles. I showed earlier where we have a track that the beta particle leaves, and we want to estimate where the interaction, where that beta particle first interacted with our scintillator. If we can do that, we can further improve the spatial resolution. And just in conclusion, I'd just like to acknowledge all the many people I've been able to work with throughout these number of years, collaborators here at the Center for Gamma Ray Imaging, College of Optical Sciences at University of Washington and Fred Hutchinson Cancer Research Center, collaborators at the University of Medicine in Mainz, Germany, and collaborators at radiation monitoring devices. It's been great to work with so many people and develop these applications. And thank you. Quantum, we're identifying each individual